Okay, welcome back for the second part of this exciting morning. Our next speaker is Laure Soulier, who is Associate Professor at Sorbonne University and a researcher in the machine learning team of the Robotic Laboratory. She's interested in leveraging neural language models for natural language processing and information retrieval, with a particular interest with conversational search systems and foundation models for the text generation. The title of her talk is Behind the Journey of ChatGPT, an overview of large language models and their capacities. Laura, the floor is yours.
Thank you. Good morning, everyone. So thank you for the invitation. This is a really pleasure to be here today. So I will talk about large language model and explain some technical parts behind language models. Don't be afraid, I will be as pedagogical as possible with images and so on. So we all know generative artificial intelligence, and we know that we can generate different type of information such as text, images, also music, and also we have seen in academic papers that we can generate levels of video games. And what is behind generative artificial intelligence is language models. So first, I will try to let you understand what are language models, large language models, and what are the technical mechanisms behind them. So first, the objective of language model is to model the probability of sequence of items. Those items can be words, characters, a subset of words. You have here an example in which I have the beginning of the sentence, and I would like the language model complete this sentence and estimate the probability of different words. To do this, the language model needs to capture the semantic of words thanks to word representation. What they do is that they build a latent space, which is called also semantic space, is different, a lot of dimension. Here in the figure, you have only 2 dimensions, but imagine we have more. And they position, we position the word within this latent space according to the co-occurrences within text. And therefore, we can identify the semantics. So we have we have a representation for each word, and then we can estimate the semantic or the semantic relationship between words according to distance, for instance, a cosine distance. The main architecture we have behind the language model is transformer, which has been proposed in 2017. Before that, we also have a neural network to capture the semantic, but I will focus on the transformers. I think this is why we are now here today. In the transformer architecture, this is an encoder-decoder neural network because it captures the semantic of words within a latent space, and encoder-decoder because it encodes an input text and decodes a text according to different probabilities. In transformer, you have different mathematical functions to transform the information, and we call this feed-forward network. And we have different successive feed-forward networks within the encoder and the decoder. And we have parallel block, which we call head also. And all these components build a huge architecture with about 65 million of parameters. What is interesting in the transformer as this architecture is the self-attention mechanism, where you have an images on the right that explain the intuition behind. The objective of self-attention is to estimate contextual representation of words. This means that we compare each word in a sentence according to the other word in the same sentence, and this allows to have contextual representation according to the sentence. Actually, it captures the polysemy of words. When you have the same surface word, for instance, Washington, you can therefore distinguish the semantic when it is a man or the city. And this is really, really powerful. And this transformer architecture had led to a kind of race in the definition of a large language model. You have here a timeline with the main language models that have been proposed, mainly by big tech companies. Those are the big ones, but we have also plenty of language models that are smaller in terms of parameters. The question is how we can build those models. I told you that they are composed of mathematical functions with parameters. And the question is how we can define the value of those parameters. In the beginning of the process, we set those values randomly. So we have a network that can compute mathematical transformation with random values. And Philippe has said this morning that we train this model with examples. So we provide massive corpus of data and we feed the network with different examples, a lot of examples. And how it is trained, we use the principle of language model to predict the probability of a word given a sentence. So for a sentence in a document, I give only the beginning of the sentence, and I expect the network to predict the next one. I told you that they are in the beginning random values for parameters. So in the sentence here in the example, if I provide it's raining, maybe the network will answer apples, dogs, rain, cat, and so on. What we do is to correct the value of the parameter according to an algorithm called backpropagation, and we can update when we notice that the network makes an error in terms of prediction. And we do this mechanism several times, thousands, billions of times, according to different examples we have in the data set, and we repeat it. And we hope at the end that the network will provide the good probability for a term and then provide the good terms in the prediction of the next sentence or of the next sentence or of the next tokens. All of this figure illustrates the mechanism of training a neural network. And then once we have done that, we freeze the parameter of the model, and then we can reuse it at the inference step in a production setting, for instance. And this is what you do when you use, for instance, ChatGPT. You provide any sentence or any question, and then it predicts the answer you would like or the end of an answer and so on. The quality of data is very important. We have seen, I will explain also later, but we have seen in ChatGPT that there is an important part of human annotator to clean the data set, to clean the data and also the different answers. And the type and the variety is also important. Philippe has also mentioned a foundation model in which we have different type of data, including text, images, and so on. I will also add, I think he has told, but code, because having code also has shown interesting properties in terms of language model. And for images, when we add images and we align images with text in language model, in the training of language model, this allows to improve the semantics of the words. When you have an image and you train the model so as it can answer to a different question, then it can map the different functionality of the words, the different action an object can do in the scene, and what is the context in the scene, and this is really important for the semantics. You have here also an example of the gap between ChatGPT, which is built on GPT 3.5 and GPT-4, when we ask those language models to draw a unicorn. You can see the gap. Obviously, on the right, I am not saying that this is a unicorn or the perfect drawing of a unicorn, but at least it rather looks like as a unicorn than in the right side, in the left side. So now I think, I assume, I hope you have understood how language models are trained, how they can be used. And I will highlight some interesting properties of those models. The first one is the scaling laws. I have mentioned that the number of parameters is very huge in transformer regarding the smaller language model. You have on the left a figure with the increasing size of language model in the time. Obviously, the scale of the ordonnée is in a logarithm scales, but you can notice that we are going to race into increasing the size of language model. And some academic papers have shown that when we increase the number of parameters, it allows to reach good performance level earlier than in a smaller language model. This means that we need fewer data points in the training instance, and also we need also fewer optimization steps. The second property of language model is prompting. I think it was in 2019, GPT-3 introduced the prompting mechanism in which you can formulate the task you would like the language model do to solve when you provide an input. You have here an example in which I explicitly ask the language model to translate a sentence into a given language, and then it can provide the accurate translation of this sentence. Obviously, the challenge is to write the good prompt. Philippe has mentioned meta prompt with specific characteristics. So this is a real challenge to have accurate and effective language models. And an interesting implication is that every task you would like to do goes into a generation task. Beforehand, we have dedicated a language model or dedicated architecture with an upper layer, a layer on the top of the language model in which you can specify this layer for classification task, prediction task, and so on. For now, what we do is to only feed the data as input, and then let the network generate the next token, which can be the expected classes, the expected prediction. And I think it changed the games. And particularly what is interesting is that in the prompt, you can also mention different examples, and we call that in context learning. This means that we only provide to the network different examples, and we don't retrain the model according to those examples. You have here an example, so you have images and text, but you can also imagine you have different example only with textual information, in which you have question, answer, question, answer, question, the beginning of the answer here, which is this person is like, and we hope that the network generates the accurate emoji related to the figure we have as an input. So we will discuss about this later, but in context learning is very efficient, but sometimes also we would like to adapt the language model to a specific task, specific data set. And what we do now is to consider large language models that are available to public, has a kind of general knowledge, a basis of knowledge we can use as an initial setup for our task, dedicated task. And then we fine-tune the model according to our data set. This means that we continue to update the model parameters according to our data. For adapting language model, we can update the whole set of parameters, but also only a part of the parameter, and also adapt with instruction learning. That means so that we only adapt the part in which we explicitly mention the task and then provide the input, and we only we identify a small subset of parameter we would like to update. Here, an example of what ChatGPT of OpenAI has done. He has fine-tuned a large language model, which is GPT-5, which is in the step 1, in which they have identified this language model. And then they have fine-tuned with dialogue data set dialogue data, often built by humans. They have updated the model parameters, and then they have continued to update the model parameter with reinforcement learning to provide more accurate response. I won't go into detail for this training, but just to show you that ChatGPT is a specific example of how we can fine-tune large language model for specific tasks, or also general objective or more accurate response generation. For now, I have mentioned that language model predict the probability of the next word according to a text input. The question is it just a simple task, a task of simply predicting the next item according to an input? What we have noticed, so you can see that we have the same figure with Philip, because this is a really famous figure. When we increase the number of parameters of the network, we have noticed that the model is able to solve more and more tasks, even if we have not mentioned those tasks within the training procedure. The network is simply trained with the next token prediction task. And what we assume is that in the next token prediction task, the network learns the grammar, the verb conjugation, the knowledge of the semantics behind words, but also, I think some paper mention it, some meta patterns that can be how we can formulate a paragraph, a story, how we can list items, for instance, and how we can reason to solve a task. A particular example of meta pattern here is chain of thought, also already discussed this morning, but just to show you that when you have this task for question answering, in which we hope that the model will do some computation in terms of numbers, so some addition, multiplication, and so on. When you don't mention what it explicitly expected, the model fails. But when you provide some example of reasoning of that you expect, doing some addition between numbers and so on, the model is able to reproduce this pattern, not the exact computation, but at least to capture that you are expected those numerical reasoning, and then to do them with the accurate number and the accurate operation. Interestingly, also, is the last case on the right here. We do not provide example of numerical reasoning, but we start the answer by let's think step by step. And what is interesting is that the model is able to capture that we are expected a reasoning, a step-by-step reasoning, and then to provide those information in the answer. And this is really interesting from large language model, and a really interesting properties. I think that somewhere in the training data, there are step-by-step word sequence, and according to the long range context, the model is able to capture what it means and what is produced in the text. Okay, so I've said a lot of interesting properties of language model, and I just would like to finish with some limitations. This is not maybe exhaustive, but I will point out the main ones. The first one is about the faithfulness of the generation. Language model predicts the most likely terms according to an input sentence, and sometimes it fails. We call that hallucination. It induces hallucination. What we have to highlight here is that when you predict the next token in a sentence, this is a likelihood, not a faithful text generation, but this is likelihood, and that's why sometimes we have hallucination. Also, language models are not grounded online directly with information source. All the information is stored in the parameters of the model, and therefore, as the information evolves with time, we need to do something in the model to evolve the parameter. And for now, this is actually worked in academic paper and also in company, but this is not often noticed in the public language model. And we have seen that, for instance, ChatGPT provide bright response, but also make mistakes. And we cannot predict when it makes mistakes. And also this is, I think, something we need to work on what we expect from a language model. Should it simply generate a text, but also alert people of when the generation is uncertain. Here you have an example where if you would like to identify objects in the scene, do you expect that a computer vision model recognize Adele? If you look better on the image, you can see that it is not Adele because either the mouse or the eyes are on the reverse side. And we hope that the language model we say it looks like, but actually it's not. And I think it should be the same with text generation model. In terms of stability, when we do some change in the prompt, we can have very different change into the response generation. And this might be particularly critical when you have critical information, non-ethical information, and so on. We also lack explainability. We have huge vectors to model the world. We have a huge model with a billion or sometimes trillion of parameters for the GPT-4. And what we see is that are the most likely terms, but we don't know why the model, for instance, generates a sentence as an active voice rather in a passive or the opposite. We have some mechanism to highlight, to generate explainability, and I think we have to work better on this. Oh, excuse me. Yeah. An actual also limitation is the transparency. We need to work on this to have better insight on the model we use in real life and in the society. Having, for instance, open source code, scientific articles that describe how the model is learned, what are the data, how we can also, how they reuse the interaction we have with the system. In terms of the data, this is really important to have those information. For instance, here, you have an example in which we ask ChatGPT to write a Python code to describe what is a good scientist. And one output, maybe this is solved now because it has done a lot of noise, but one of the outputs in the early beginning of ChatGPT is that a good scientist was a male and a white male. And this is probably due to the data because it is based on web data. We have, I think you can identify who produced information on the web, and particularly which community, which part of the web, and also this has an impact of the text generation. If we go larger on generative AI, we also have to think about the perception before this last month or before mid-journey, we thought that when we see an image, it was the truth. And we all know that this can be different now. And therefore, we have to change our perception. We discussed also this morning about anthropomorphism, whether a language model can be assimilated to humans. I just would like to provide you 3 examples here in which we can ask language model to complete the beginning of the sentence. As human, we know that the first one is related to an historical event, and then we will identify those the accurate information. Then in the second one, this is a famous sentence from a movie from children, so we can assimilate the knowledge. And the last one is this is about Lord of the Rings. But what we have to be aware is that when a language model answer to those information, it predicts the next item. This is the same behavior for those 3 different examples. And I will end my talk with the last slide, maybe an open question here to share maybe an insight. In 2013, when Google has introduced the Google Knowledge Graph, which is used as a basis of web search, we have noticed a significant decrease of Wikipedia audience. And an open question to end this talk is, if we use generative AI, what will be the business model of the web in which we provide sites and some creators of the content site are earn money according to the visit, and maybe we won't visit to those websites. So I think also it hurts the economic model of the web. I don't know if it's good or not, but just to open this question. Thank you for your attention. I will be happy to answer different questions.
Thank you. Thank you very much, Laure. So maybe I will start with a question from online, and I see there's a hand over there. But perhaps first the online question. Is there an interest to keep large language models smaller to make it work better for a precise domain and making it less general or vague or better in some tasks?
Difficult question. What we notice is that when we increase the size of network, we have very good performances, but I have not mentioned, but maybe I have something here. The last one is also the computational cost behind language model. So here for just ChatGPT, for training those model, we have done a kind of a small exercise in our lab to estimate the surface of GPU used to train a model, and this is actually the surface of a house. This is smaller when we use a model in production, obviously, but I think large language model has this limitation. We have very good solution on the cloud also to use a language model, but we have to think also to design a small model in terms of environment and also interesting properties, but this is really difficult. What we have noticed in the literature is that designing smaller model directly is not really effective. And what is effective is to start from large language model and then try to reduce the size of the language model to do some pruning of the parameters and so on. And we have also to work on this. Do we lose generalization and effectiveness? Maybe, but maybe we can have a good balance in terms of computation and also effectiveness. It depends on the use case, obviously. Yes.
Okay, we have a question.
Thank you so much for your talk. You mentioned the importance of data and data quality in training those large models. And you also mentioned the required human intervention in cleaning and tagging the data. So my question is, what are the alternatives the AI community is looking into to reduce the human intervention? Are self-supervised models or semi-supervised models a good or a promising alternative?
Yeah, actually, having an annotator is very costly, and we know that in OpenAI, they are very they are a lot of annotators. We cannot do this either in the academic side, so from my side, but also in some companies. And we have to think about generating labels is a solution, but we have to identify also that if you generate wrong labels, this is kind of vicious circle. But in some work, it has shown that it can improve the effectiveness of model if you have a good balance between clean data and also generated one. And self-supervised is also an interesting way. Reinforcement learning might be also a good solution, because we maybe a few annotated data, you can learn an algorithm to estimate the scores of the output as done in ChatGPT, and then fine-tune the model according to this. But yeah.
Maybe if I just comment on the two last questions. I invite you to look at a research paper on Microsoft Research called ORCA, or CA. So we trained a new small model. So it's a foundation model with only 7 billion parameters. on par with ChatGPT 3.5. And it was trained using both GPT-4 and GPT 3.5. So basically, we asked GPT-4 to train the model, and we asked GPT 3.5 to do the supervisor role. So looking at the way GPT-4 was training the model to avoid bias, which could be put by GPT-4. So it's basically synthetic data generated by GPT-4 and overlooked by GPT 3.5 to give the birth to a small 7 billion parameters model, but with a very large capability. So that's one target, I think. So I invite you to have a look at the paper.
Thank you.
Thank you very much for your presentation. Brilliant one.
Thank you.
I have a question. Usually when you use neural nets, you can have too much complexity in the neural nets. So if you have an easy problem and the model is too big, too large, then the result will not be good because it doesn't generalize enough. Do we know when LLMs will hit this barrier, or is this far out of sight and we actually don't know if we will ever hit that barrier?
I don't know if I have the good answer to this question because this is a complex one, but we have interesting properties in language model in terms of semantics, in terms of reasoning, but obviously we don't always need those large language model or large models to solve simple tasks. But I don't know actually if we maybe by designing smaller language model, if you do pruning and so on, you will hinder some extrapolation and gain into generalization for smaller tasks. But I don't know. I think it's a difficult question, and I don't know if we have the answer right now. No.
Thank you.
Okay, I have another online question, maybe the last one. Can we use situation awareness, especially perception and comprehension concept with large language models?
Yeah, maybe my answer will be biased with my lab. I am in a robotic labs and we are working on a language model that can encode some perception behaviors. What is done is to train the model with trajectories of robots, sensors, information from robots, and associate therefore words with those perception cues. This is done in the literature. We have started to work this, I think, 2 years ago. And there are plenty of papers and plenty of models with that from big tech companies and also from academia. We can do it, but I think we can improve them again and again. For now, for most of the models are designed to generate planification for robots, generate a sequence of instructions, and also performing action. The use cases are for now quite limited. And we work on open-ended learning, so having a generalization over that.
Okay, thank you very much.
Thank you.
Let's thank Laure again.